So let's have a look at two applications to these types of problems. So I'm just going to come down now and have a look at an angles of elevation and depressions question. So let's have a look and draw this diagram. From his first position, Justin observes that the angle of elevation to the summit of a mountain is 10 degrees. So we'll call this one the first position, and we'll put the summit of the mountain up here, and so we have this diagram, and that is 10 degrees. Now obviously that's not 10 degrees, and I'm drawing a not to scale diagram. From his second position, which we'll say is here, we have now an observational angle, or an angle of elevation, of 14 degrees. And of course the question then asks, how tall is the mountain? So we'll also need this height of the mountain component here, and I'll call that h. And of course there is this extra piece of information. From his second position, 500 meters closer to the mountain. And actually that closer component is really important, because from the first position here, he could really walk in any direction and then claim the 14 degrees, and we wouldn't have an understanding of exactly where he is compared to where he was and where the mountain is. So 500 meters closer to the mountain. Now we need to find height, but in that right angle triangle here, we have only one piece of information. And in the large right angle triangle, we also only have one piece of information, that 500 meters is not a complete side. So we do have lots of options, and we can do this question predominantly by right angle trigonometry and solving simultaneous equations. But instead, we could also do it by labeling this side as x, solving for x, and then using x to solve for h. So let's have a look at, first of all, solving for x. And as x is green, I'll highlight the triangle we're going to work in green. So let's work with this triangle. Now, of course, x is our unknown, so I'm going to write down x, the thing I want to find, over sine of 10, so that's opposite, is equal to the other two known quantities, 500 over, now we have a little bit of a problem, because I don't know the opposite. But if we have a close look here, that 14 degrees implies this is 166. And of course, if I know two angles in a triangle, well then I know the third. 180 minus 10 minus 166 means that this is 4 degrees. And so now I have over sine 4. And so x is equal to 500 over sine 4 times sine 10. And of course, I can very quickly calculate that, and I get 1244.67 meters. Now I'm a bit worried at the moment. This is a very tall mountain, but that is a diagonal length. So it's not actually the height, and we're not quite there at the height yet. Now let's have a look at this blue triangle. And in this blue triangle, I have x known, and I have 14 degrees, and it's a right angle triangle. So I have this. Sine of 14 is equal to h over x, and that means that h is equal to x, which is 1244.67 times sine 14, and that of course is 301.114. And I'm pretty happy with that height of the mountain. It seems appropriate for the not to scale diagram that I have. So there you have it, an angles of elevation and depression, quite reasonably complex contextual problem. And lastly, I have a bearings problem to work with. So let's start again by drawing the diagram. Now I've read the diagram ahead. I have from ship S, P and Q are on bearings 320 and 075 respectively. So that means that P matches 320 because they're in order. That's what respectively means. So I know that 320 is in that direction and 75 is in this direction. So I'm going to start with S down here and draw a little dot. I'm going to draw just a rough line here which will take me to P, and I'm going to draw a rough line here which will take me to Q. And I also know that P is a little bit further along than Q, so that's 7.5 and that's 5. And the question says find distance PQ. So I drop a dotted line along here, straight to Q. This is distance PQ, and that's what I'm trying to find. But to do anything, I'll need an angle. So first, let's just do, we've been calculating bearings, so this should have a north component. And now that I've got that, and I know that the ship P is on a bearing of 320, well, that leaves 40 remaining for this angle, because 320 is the whole way around to there, and 360 is the total rotation. And of course, I also know that this one's on a bearing of 75, so there's 75, and this means that the entire angle is 115, 40 plus 75. So now I have a triangle with side length 7.55, angle of 115, and the opposite side is what I'm missing. So that means that I have 1, 2, 3 known sides and a known angle, so I'll be doing the cosine rule. I want to find PQ squared, and that of course will be equal to 7.5 squared plus 5 squared minus 2 times 7.5 times 5 times cosine rule of 115. And I evaluate this now and I get 112.946. Now don't be afraid to be a little bit worried here. How could it be that that's 5, that's 7.5 and this is 112? But of course now we recognise, and it's a very common mistake to forget to do this, that we have to take the square root. So it's equal to the square root of 112.946, and that of course is equal to 10.63 kilometres. So there we have it. We have first of all some work on the sine rule and the cosine rule, the derivations of them, and some examples, the over triangle rule, and a couple of applications. This video may have been split into 2 videos. I don't want them to be too long, but they do pair up quite nicely. So make sure you understand the prior concepts before you read through this. All the best and good luck.